All right, so let's begin our second session. So the next speaker is Nathan Seiberg, and he'll tell us about anomalous continuous translation.
Thank you. It's a pleasure to be back at Princeton. And of course, I thank the organizers for inviting me to this talk and for putting together this interesting conference. It fell already? Can you hear me? So I don't see direct relation between what I'm going to tell you and confinement, although motivated by various conversations here, I already see some possible directions. But it is a very amusing phenomenon that exists in continuum quantum field theory, and as such, I thought I would share that with you. This work is based on two papers. One of them I wrote last June, and another paper I'm writing now, which provides a streamlined and broader description of the same work. So if some of you heard me give talk with a similar title before, the perspective will be a little bit different, this one, in this talk. So what will I be talking about? I'll talk about a collection of some models in continuum quantum field theory. I'll specify exactly which models I'm talking about. And I put them all on a spatial torus with periodic boundary conditions, to be concrete. So only torus with periodic boundary conditions. And therefore, I will discuss translation symmetry, which we always take for granted. But the models will all have something special, which will ruin the translation symmetry in an interesting way. So two classes of models that we'll discuss. One is a U1 gauge theory with constant charge density. So A is the gauge field, the dynamical gauge field, and the ellipsis represents scalars, fermions, kinetic term for the gauge fields, etc. So this looks like an innocent coupling. It's not gauge invariant, but under gauge transformations, transforms by total derivative, so it might be okay for a specific value of rho. I should also say that the equations of motion of this just say that by differentiate with respect to AT, Gauss law is modified. And since Gauss law is modified, it puts a constant rho on the right-hand side of Gauss law, and therefore we have constant charge density. This looks very innocent, and this Lagrangian with such a term has a long history. I will review a little bit of it later. Closely related models occur when we have certain sigma models. Again, I'll define them more precisely later, which contain a term with a single time derivative. An example would be the O3 sigma model in any number of dimensions. The target space is S2. We use projective hystereographic coordinate Z. So Z is the complex plane. And it's common to add such a term to the Lagrangian. This is a term with one time derivative. And it even has a name, which shows that it is a standard term to add to the Lagrangian. It's called either the Berry term or the West-Zumino term.
So it's from the very beginning not Lorentz invariant.
It's not Lorentz invariant. The theory is not Lorentz invariant.
But it also, if it's a kind of analog of asymptotic, whatever, it could be that rho is could be screened by.
We'll discuss all that, and if we get hung up on slide 3, I can promise you we'll not get to the story. But you're completely right. This is not Lorentz invariant. But I'm soon going to discuss in what way this model is related to another model, which is Lorentz invariant. I should say that there are materials in the world that describe that. This is the Lagrangian that describes a ferromagnet. So wherever you see a ferromagnet, you have this Lagrangian. So it's not something pulled out of a hat. And all these models have some common features. That the classical Lagrangian is not well defined. We saw that with the gauge theory. There's a term A sub t, and in the nonlinear sigma model, the behavior at infinity is bad, so we need to use patches and to work a little bit harder to make sense of them. But the equations of motion are perfectly fine, and the model appears to be translation invariant. There was not, even though it was not Lorentz invariant, there's no explicit x dependence in the Lagrangian. When we go to the quantum theory, we need to define we have to be more careful about the definition of the Lagrangian. And the first compromise is, well, at least the action should be well defined. And if we fail that, at least the exponential of the action should be well defined. And we are quite familiar with that. So we need to give a definition of the exponential of the action. And we want to do it in such a way that the classical equations of motion are not changed. That would mean that we still start with the same classical theory and we just put a little bit refinement to define the quantum theory. And often, as we do that, we find that there's new data, like theta parameters. These are parameters which are not there in the classical physics. They appear in the Lagrangian, and they modify the quantum physics. In our case, in all these models I will be discussing, this additional data that comes in the quantum theory explicitly breaks translation symmetry. And we cannot turn it off. It explicitly breaks translation symmetry, and not only that, as I will show, the discrete translation symmetry becomes non-abelian. So the models I described before have only discrete translation symmetry, and the translation symmetry is non-abelian. But I should say from the outset that many of the results I'll present are known in the literature. I'll give the references, they're pretty old. But there's huge controversy about the interpretation about what's going on here. And there was a lot of confusion. Is it an artifact of an underlying lattice? What happens if you take the infinite volume limit? Is the effect classical? Is the effect quantum? Et cetera, et cetera. And what I'll present here is a unified treatment of this large class of models. And I'll present it as an Adler-Bell-Jaquev anomaly in translation, not ABJ anomaly in the target space, not an ABJ anomaly in a global internal symmetry, but instead an ABJ anomaly in ordinary translations of space. So that's a summary of the talk. And now we'll go to work. Before we go to work, we always need conventions. So these are my conventions. I have flat torus in D spatial dimension. D will be the number of spatial dimensions with some identifications of the coordinates. This is the volume. Lorentzian time will be T. And I'll go back and forth between Lorentzian and Euclidean signature. I'm sure this is not a problem for this audience. So the first model would be dynamical U1 gauge field with constant charge density. As far as I know, this model was first discussed by Fischler, Kogut, and Susskind in '79 in the context of the Schwinger model. They were interested in the Schwinger model in the constant background charge, and they discussed exactly this model. Their interpretation was not, of what's going on was not quite complete. The model was kind of dormant for many years, and Max Metlitsky picked it up when he was still in undergrad. It's quite impressive, in '07. And he clarified some of the confusions in the original paper. And there's been some follow-up on that later. So this is really a very old problem. So again, this is the Lagrangian. And as I said before, the classical equations of motion are gauge invariant. The Lagrangian is not, but the equations of motion are. And what they state is that we have constant charge density. That should be easy. Now, when we go to the quantum theory, what people often say is the Lagrangian is not gauge invariant because it's transformed by d by dt of the gauge parameter. So we go to Euclidean space and we consider gauge transformations that wind around the Euclidean circle, and they quantize the charge. Intuitively, this is clear. If the charge density is rho and the volume is v, the total charge is rho times v, and that should better be an integer. So the coefficient here is an integer, and we already see something quite peculiar here, that the large volume limit of this model is going to be a little bit interesting because the local Lagrangian depends explicitly on the volume. But it is what it is. That's what we would like to study. And naively, the quantum theory is now gauge invariant because we quantize the total charge. So we work in finite volume. The total charge is quantized. The Lagrangian seems to, the quantum theory seems to be well defined. And so gauge invariant. And it has continuous translation symmetry. What we will show is that, in fact, this is not the case. This theory, as I presented it, is not translation invariant. And it's not translation invariant in an interesting way. I see some faces look puzzled, and the more puzzled you are, the happier I am. So what should we do about this term? So we need to define the exponential of the action. That's what we need to do. And there are several ways of doing it. The proper way to do it is to use fancy math that I'm sure all of you are familiar with. It comes under the name of pre-quantization or differential cohomology. But since all of you are experts in that, I will not take this route. So what I did in the paper was to be very low, to give a lowbrow version of this. I covered space-time with patches. In every patch, I wrote a A mu, and then there were transition functions between the patches on the overlaps, and the term has to be defined such that we integrate this data over all of space-time. And that's the approach I took in the paper. I'm not going to do it here. Instead, what I'll do here, I'll present another approach, which can be viewed two ways. Number one, this is a trick to avoid the use of differential cohomology, where I'll use a result from differential cohomology that all of you know, but you don't know that it really follows from differential cohomology. And it might also point to a deeper structure, which I will describe. So our goal is to define this thing. That's our goal. So what are we going to do? We need to define the action. Let me first set k to 0. Now, this I cannot complain. This is a Lorentz invariant theory. So this is a good old-fashioned Lorentzian theory. And it has a d-2 form magnetic symmetry, a d-2 form global symmetry, often referred to as the magnetic symmetry, whose current is dA. That's a symmetry of the problem. The conservation is the Bianchi identity. And the rule is that whenever we see a coupling constant in the Lagrangian, I've used this rule many times in my career, whenever you see a coupling constant in the Lagrangian, think of it as a background field. And think the theory more broadly as a function of all these parameters. And in our case, we have a symmetry, so we have to couple it to a current. We have a symmetry, we have a current, and therefore we have to couple it to a background gauge field, big A. So we're going to have two gauge fields. Little a is the dynamical gauge field, and big A is something that I pulled from outside. This is a background field. So let me give some examples. In one plus one dimension, this term is a theta term. So we have a gauge theory in 1 plus 1 dimension. We might as well add theta, because this is something we can turn on, so we might as well turn it on and evaluate everything as a function of theta. In higher dimensions, there's a magnetic symmetry, so we can write big A, wedge d little a, so this is a standard Chern-Simons coupling. And we can also go to higher dimensions with higher gauge fields. So now we set k to 0, we identify the symmetry, we couple it to background fields, and now we would like to define the theory coupled to a background field. So that's our goal. And in general, this is a Chern-Simons coupling. So we would like to define the exponential of the Chern-Simons coupling. So this is where we started. And I write plus dot 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 because it needs to be defined. We can also integrate by parts and write it this way. And again, they are the dot dot dot. Now one might argue that from the first expression, this is independent of the zero mode of little a. From the second expression, it is independent of the zero mode of big A. And therefore, one might argue that the answer is independent of the zero mode of both little a and big A, which some people laugh in the audience because that's not true. And we all know that this is not true. And the stuff is really buried in this dot, 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 which deeply comes from differential cohomology, but I'm just going to quote the answer. So we're going to use the fact that despite appearance, the constant mode of big A or little a is there in the Lagrangian. So now that we have that introduction, we're going to couple a particular big A. So we said the theory should be viewed as a function of this background big A, and I'm going to turn on a particular big A, one that has a constant magnetic field. So dA is this object, and notice that big A, in order to have constant magnetic field, must be x-dependent, because otherwise you can't have a constant magnetic field. So the way I will break translation symmetry is I'm going to turn on this A. This magnetic field means that big A depends on x, and through that, translation symmetry will be broken in the theory. So let me give an example. Imagine we are in 1 plus 1 dimensions. We already turned on theta. So let theta be linear in x. So we take the same Schwinger, or the same 1 plus 1 dimensional gauge theory, fermions, bosons, what have you, and let the theta parameter be linear in x. If we integrate by parts, we find a term linear in AT. So the term linear in AT is defined through theta, which is linear in x. And in 2 plus 1 dimensions, this is ordinary magnetic field, and it's a high form gauge field in higher dimensions. So when we do all that, our coupling, little a, dA, appears the coupling we would like to study. So our goal was to study this coupling, and then I said this coupling should be viewed is due to a background gauge field big A, and it appears like it's independent of X, but when we write it this way, it depends on X through big A. So this is the upshot. This means that through the explicit X dependence of big A, the coupling we are interested in is not translation invariant. So this was a very roundabout way of doing it. We could have done it using differential cohomology, and then it's almost straightforward. We could do it in terms of patches and transition functions. You get the same answer. And here I presented it from this perspective with the background gauge field, and I derived the same answer. And explicitly what it means is that if we shift xi by a constant, we perform translation transformation, this term we would like to define is shifted by a term proportional to the dynamical field strength, the electric field of the dynamical gauge field. So notice as a sanity check, this is a total derivative, this term is a total derivative, and therefore it does not affect the equations of motion. So indeed, classically, the theory is perfectly fine and translation invariant. But in the quantum theory, we have this peculiarity that when we perform a translation transformation, it shifts the electric field it shifts the Lagrangian by a term proportional to the electric field. So that's a statement that this is totally harmless in the classical theory, and the subtlety is in the quantum theory, and it's not because there are quantum loops, and it's not because we had to regularize anything, and it's not because we had fermions which are subtle. It just comes about from the need to define the exponential of the action. That's what drives the show here. So the quantum theory does not have this translation symmetry. Classically, we had U1 in each direction because we are on a torus. But instead, since this thing is quantized, since the electric flux is quantized in subunits, the U1 is broken to Zk. So K was the total charge in the background, and now we have Zk translation in each direction. And I'm going to interpret that as an ABJ anomaly in translation. And I can give more evidence that this is the proper interpretation of what's going on here. But if we take a definition of ABJ anomaly, is a situation where the classical theory has a symmetry, which is broken explicitly in the quantum theory that fits the bill. So carefully defining the quantum theory tells us that we don't have translation invariance. Instead, we have only discrete translation invariance. I emphasize this is explicit breaking, not spontaneous breaking. So it's not that the crystal was formed, because in a crystal, the spontaneous breaking is the breaking of translation symmetry is spontaneous, and therefore we have phonons. Here there are no phonons. This is explicit breaking. And for this audience, the better analogy is to say that there's a U1 symmetry naively, but in fact there isn't a U1 symmetry, and therefore the eta prime is not massless. So the breaking of translation symmetry here is analogous to the fact that the eta prime gets a mass, except that the derivation was a lot more elementary. Notice also that the thing that activates it is instantons here, where we have total flux of the electric field. So the analogy is quite similar to the eta prime problem. And if we go to higher dimensions, these discrete translations along the different directions, I don't do the algebra here, they do not commute. The commutator is the magnetic field in the direction we move. So translation in X and translation in Y, not only are they discrete, they also don't commute, and instead we get the magnetic field. Notice this is not the background magnetic field that I turn on. This is the magnetic field of the dynamical field, and therefore this is not a central extension of the translation symmetry. It's an actual violation of the symmetry. The symmetry becomes non-abelian. So what I argue is that with constant charge density, the classical U1 symmetry is explicitly broken to a discrete subgroup, and furthermore, that subgroup is non-abelian extended by the magnetic symmetry. This suggests a large generalization of what I said. Consider any theory which has a D-2 form U1 global symmetry. So let me unpack this definition. So this is a large class of continuum field theory that I promised at the beginning. Whenever we have this symmetry, the effect is present. The D-2 form U1 global symmetry means that there is a conserved current with integer periods. And the fact that I needed it to be topological, I said that dj equals 0 without using the equations of motion. So locally, j equals d phi. And in our gauge theory example, j was the field strength of the dynamical field, and phi was the dynamical gauge field. So here are other examples which have that symmetry, just to show you that I'm not talking about the empty set. The target space is S2. We have a nonlinear sigma model, O3, and that has such a symmetry. I'll soon discuss this model in more detail. If the target space is T2, this happens in 1 plus 1 dimensional. In 1 plus 1 dimension, it leads to the C equals 2 CFT. We can also let the target space be a Calabi-Yau manifold. It also has such a symmetry. So in all these models, we have such a symmetry. So I'm really discussing a very large class of models with interest in different branches of physics. So we now repeat the previous discussion. We have a symmetry, we couple it to a background gauge field. We integrate by parts to write it like this. We specialize to A, which is a constant magnetic field. That is very nice with PowerPoint. I can just copy the previous slides.
And what if we tend V to infinity?
I'll discuss that. There are lots of questions that can be asked.
Okay.
Please hold on. I'll soon give a list of questions and I'll answer whatever
Okay.
I can. I promised you we would relate that to a theory with Lorentz invariants, and I think I did. So this is the Lagrangian. Take any one of these theories. You can add such a term to the Lagrangian. And classically, it's translation invariant. But since phi t is not well defined, we get anomalous translations. We have only discrete translations, and the symmetry is extended and becomes non-abelian, which is a bit surprising. Let's specialize to nonlinear sigma model. First of all, there's a large class of models that exhibit that. Any nonlinear sigma model whose target space is 2 cycles has these phenomena. For example, the O3 sigma model. And there's a way to describe. And there's a way to describe all these models, which is quite familiar in the CP1 model, by making the target space larger. In the S2 case, I'd make the target space S3 and make the U1 gauge and couple it to a U1 gauge field. And then the discussion of the nonlinear sigma model is essentially the same as in the U1 gauge theory. So this term in the nonlinear sigma model, if you write the nonlinear sigma model as a CP1 model, this model is the same as having constant. So it's the same as writing the CP1 model using a U1 gauge field and turning on this coupling, because the discussion of the U1 gauge theory applies. Now let me specialize further to the case where the target space is a symplectic manifold. This is the case, say, for example, in S2 or T2 and many others. In that case, phi, this object phi, has a name. In the target space, it's called the Liouville potential. And in our case, it's the pullback of the Liouville potential to space-time. And in the other thing that is special about symplectic manifolds is if the target space is a symplectic manifold and we turn on this term, all the terms with 2 time derivatives are negligible and we can forget about them. And we end up with a Lagrangian that has only first order time derivative. That's because the symplectic structure is non-degenerate. Now let's apply it to a model of interest. I'm titled this From Antiferromagnets to Ferromagnets. So let me start with an antiferromagnet. An antiferromagnet is described in the continuum as the standard O3 sigma model. This is a textbook statement. The continuum O3 sigma model has a D-2 form symmetry associated with skyrmions. This is the current and this is the charge. And now we turn the crank and we do the same thing again. We have a symmetry, I couple it to a background gauge field, A, and I integrate by parts and so forth. And that means that I add to the Lagrangian this term, which has bad behavior at infinity, but I'm going to make sense of it soon. And again, there's huge literature on this term. It's known as the Berry term or the Wess-Zumino term. So let me take an example. If I'm in 1 plus 1 dimension, I'm just studying the ordinary O3 sigma model in 1 plus 1 dimensions. It has a theta term. I can add theta times Q. But if I make theta position dependent, I may take the same good old nonlinear sigma model and make theta linear in X. It leads to this term by integration by parts. So this Lagrangian appears to be translation invariant, but it's not, as I said. In fact, in this case, the target space is symplectic. We can even neglect the higher order terms in time derivatives and end up with a Lagrangian which is first order in time derivative and second order in spatial derivatives. And again, there is huge literature on that Lagrangian. This is the Lagrangian that describes the ferromagnet. So from this perspective, the difference between a ferromagnet and an antiferromagnet in the continuum is that in the ferromagnet Lagrangian is obtained from the antiferromagnet Lagrangian by turning on a background gauge field for the skyrmion symmetry. This is a way of phrasing the relation between the two. And if you take this broader view of quantum field theory, that it should be viewed as a function of the coupling constants, of all the coupling constants, being also position dependent, then you see that they are all members of the same family of theories. Now, in this particular case, the breaking of continuous translation symmetry is known since '86, the paper by Haldane, although the interpretation was kind of kept changing over the years about what's going on here. And the emphasis here in this talk is that the issue is in defining the functional interval. We don't have to define operators. We don't need to compute any loops. And it's really like an ABJ anomaly. So there are additional topics I didn't discuss here, which were either in the paper I wrote or in the paper I'm writing now, which address some of the questions that people here might ask, and depending on how much time I have, I can elaborate on that. One is, how can we see that from the point of view of the energy momentum tensor? Let's apply Netter procedure and see what's going on. And the story is essentially the same as with the ABJ anomaly. The energy current is conserved, no problem, but the momentum current is not globally well defined. And we can write the conservation in terms of something that is well defined but not conserved, and something else which is conserved but not well defined. So it's very similar. Then Misha's question, what happens in the infinite volume limit? And there are different ways of taking the infinite volume limit with infinite k or with infinite ratios. And there are all sorts of other ways of doing it. And they all should be analyzed, and they are all interesting. And part of the confusion in the literature is that what most people did worked directly at infinite volume and did not see where this thing comes from. And there's a general rule in problems in physics. If you're confused in infinite volume, do it first in finite volume and then take the limit. And this is the quick answer to your question. Every one of these is a few slides in the longer talk. Also, you could ask, if I have a lattice at short distances, there already are discrete translations on the lattice, what's the relation between the discrete translations of the underlying lattice model and the discrete translations that I found in the continuum? Notice that in general, when we go to long distances, the translation symmetry should get bigger because it shouldn't be just discrete, it should become continuous. What happens here is that naively it becomes continuous, but in fact it becomes discrete, but it's finer step than of the underlying lattice. And this whole thing is connected to other topics. In fact, this is how I got into all that. There are 't Hooft anomalies in the problem and related to Lipschutz-Matisse theorem. And I was struggling with paradoxes with ferromagnets and the Lipschutz-Matisse theorem, and that was the resolution of the paradox. So this is how I got into this problem. It's also good in checking dualities, because if we have two models that we claim they're dual, we can turn on background gauge fields and check that still the answers are the same. In particular, we can turn on this background gauge field and take models that are perfectly innocent, perfectly translation invariant, but when we turn on these background fields, this thing happens, and that should happen the same way on the two sides of the duality. And it does indeed happen the same way on the two sides of the duality, but for different reasons. So we land on our feet. And there are a few other results like that. Since I need to finish, we discussed a large class of models defined by having a topological two-form U1 global symmetry. There's a symmetry, we couple it to a background field, and then we specialize to a particular background field. And there were two classes of special cases, which I said are actually related to each other. One of them is a dynamical U1 gauge field with constant charge density, and the other is certain nonlinear sigma model with a term which is first order in time derivative. And one of them is the special case of that is the Lagrangian for the ferromagnet. So this is to show that it looks very peculiar, it looks very esoteric, but there are actually many examples with a lot of interest with huge literature on the subject. And in all these cases, the U1 to the D translation symmetry of the classical theory is broken in the quantum theory through an ABJ-like anomaly. I said ABJ-like because it's not in an internal symmetry, not in a chiral symmetry, not even in internal symmetry, it is in the space symmetries of the model. And that's what I said, we have anomalous translations, only discrete ones, and the symmetry is extended and becomes non-abelian. Thank you.
This may be naive, sorry about that. If we consider the instantons, for example, in sigma model, going between different fermion sectors, I think the term you are reading, I feel like it will complexify the fugacity of the instantons. It will give them a phase.
What are you doing the antiferromagnet or the ferromagnet?
Let's say, antiferromagnet.
Okay, antiferromagnet means good old-fashioned O3 sigma model. The effect I'm talking about is completely absent.
It will go to ferromagnet.
Okay, that means that I turn on that term.
Yes.
When you turn on this term, this is the same in 1 + 1 dimension as making theta linear in X. So that's very important that it's linear in X. So locally, it's this term. But you know, even if it's linear in X, at some point it jumps. So there's something subtle at the point where it jumps.
Exactly.
The effect I'm talking about comes about from the points where it jumps. So there's a way of saying it more systematically, that this is what this differential cohomology is doing, or you could do it with patches. And what happens there is the translation symmetry is broken there, which in hindsight is not surprising because theta was linear in X. So phrasing it this way, it's not surprising. Phrasing it the other way, it is surprising.
So we know that, for example, winding theta angle modifies instanton amplitude so much so that it may lead to, it may lead to destroying each other, destructive interference.
Well, I would phrase it differently, but winding theta angle is exactly what differential cohomology is good for. So whenever you try to write, say, even 4-dimensional QCD, you write F wedge F and let theta be position dependent, it can wind around space, or you can have also an interface. Theta is constant, then moves by 2 pi, and I keep going to infinity, and then there's an interface here. The physics around the interface, I've written many papers on this interface, and the physics of this interface is quite interesting, and the phenomenon here is not unrelated to that.
Okay.
To me, it's also kind of together with Sasha Mogorsky, we considered again CPN model or SO model, not from this point of view, but people consider they're kind of serotonin type of solution, and we proved that it's not positive energy, it's negative energy. So in consideration the serotonin type of configuration, it looks like a signal of instability, which makes vacuum state inhomogeneous. And I'm not sure that it's related to what you are talking, but I am certainly very much interested in, and we are doing this for some number of years already.
Oh, thank you. I'm very happy that somebody is interested in my work. At my old age, this is the maximum one can hope for.
But in this way, you see, the question is whether it could be realized as inhomogeneous, indeed realistic vacuum state.
Right, but the interesting thing here is that I wrote a classical Lagrangian, which if I ask you, is it translation invariant? Misha would complain it's not Lorentz invariant. So yeah, it's not Lorentz invariant, but does it have at least the Euclidean symmetry? And you would say obviously yes, right? Because it does not depend on X. And the lesson I'm saying is that if you just want to define the exponential of the action, there are subtleties there that explicitly violate translation symmetry. And I gave one interpretation of that through background field. The background field is not essential. I can do the whole thing without ever mentioning the background field and reach the same conclusion. And if it's related to your paper, I'll be delighted to, please send me the reference.
Okay.
Okay, so
If you allow that to be X dependent, is it the same as the axion field?
No, because it's not dynamical. Because I'm not integrating over all possible theta of x. I have background theta of x.
So,
one last question from Mario.
Yeah, so it's really interesting observations. So just let me make a comment. In lattice QCD calculations, when you include dynamical QED, then you have to worry about something analogous to this. So imagine you have your box with periodic boundary conditions and you put a single charge in the middle that doesn't satisfy the periodic boundary conditions on the edges. And so there's two methods that people take to generally deal with this. One is just delete the zero mode. So in the sampling of the gauge field, you can just remove the zero mode. This introduces the non-localities that I think are the analogous to the lack of Lorentz invariance. And this gives rise to volume-dependent coefficients in any types of loop calculations you do, which you wouldn't normally expect to be there. That's where that pathology arises. And the second thing people do and so effectively what removing the A0 mode does is it allows the system to relax, to put a background charge density to exactly cancel that localized charge.
Yeah.
Okay, and so then it becomes like a condensed matter problem with charge neutral material.
Right, so this what happens here in the continuum is similar to the ladder thing.
Yeah,
So-
right. And the other thing people do is use
If you compare to condensed matter literature, I would say that this is actually not quite what they do with the Wigner crystal. With the Wigner crystal, it seems superficially the same, but it's actually fundamentally different because what you would call the gauge group in the Wigner crystal is treated as if it is R, whereas here it is treated as if it's U1 rather than R.
I'm
That's a
just
big
wondering
difference.
if what you've done provides another way to include QED into lattice calculations.
I hope it does, because we're just the same as I said to Arkady, I'm very interested if you find more applications of this.
Right, let's thank Anya, yeah?